Hey everyone, and welcome. Today, we're going to dive into what might just be the next giant leap in how we make things 4D printing. This is a technology that could totally reshape everything from medicine to construction. So let's jump right in. All right, let's kick things off with a pretty wild idea. What if the objects all around us weren't just static and lifeless? What if our world could, quite literally, build itself? I know, it sounds like something straight out of a movie, but that's the core concept we're talking about with 4D printing. Just take a second and really imagine that. You order furniture, it arrives in a flat box, and then it just pops into its final form all by itself. Or think about a medical implant that not only fits perfectly when it's put in, but actually continues to change and adapt to your body as you heal. These aren't just fantasies, they're the kinds of things 4D printing is making possible. So, how is any of this even possible? Well, to get it, we have to introduce the star of the show, the fourth dimension. And don't worry, we're not talking about some mind-bending physics concept here. In this context, it's just time. And adding time as an ingredient in the manufacturing process, well, that changes everything. So, where did this all come from? The story really starts back in 2013 at MIT. A researcher named Skylar Tibbetts came up with the term 4D printing. He and his team showed off something that was frankly incredible, objects they had printed that could fold themselves up when you just added a little water or heat. This was huge. It proved, for the very first time, that you could literally program change right into the fabric of an object. Okay, so you're probably thinking, isn't this just fancy 3D printing? Well, yes and no. We're all pretty familiar with 3D printing, right? It creates static, finished objects. 4D printing is the next step. It creates dynamic objects that can react and respond, and it does that by using these special smart materials. And that's the real key here. The goal isn't just to design the final shape, it's to program how that shape is going to transform over time. So, if you boil it all down, what is 4D printing? It's the combination of 3D printing and smart materials. This mix lets us create objects that aren't just sitting there. They can actually change their shape or even their function, all on their own when they get a specific cue from the environment around them. But how does an object know when to change or how to change? Well, the secret, it's in the ingredients. It's not about the printer, it's about what you're printing with. These aren't your everyday plastics. They're called smart materials. And honestly, they're the secret sauce to this whole thing. At their heart, smart materials are engineered to have a very specific, predictable reaction to some kind of outside trigger. That trigger could be heat, it could be moisture, it could even be something like light. Think of it like this. The instructions for how to change are baked right into their very structure. All right, let's talk about the key players here. You've got shape memory polymers, which basically have a built-in memory. You can print them in one shape, then bend them into another, and when you apply a trigger, they snap right back to the original shape they remember. Then you have hydrogels, which are fantastic because they react to water. And for really complex movements, you can print with multiple materials, combining stiff parts and flexible parts to create some truly intricate transformations. Okay, so having these cool materials is one thing, but that's only half the equation. The other critical piece is actually programming the change you want to see. You have to design that transformation from the very beginning. The actual process, when you break it down, is pretty straightforward. First, you design a 3D model, but this isn't just a static model. You're actually designing the entire sequence of movement. Then, you print it, layer by layer, carefully placing those smart materials exactly where they need to go. And finally, the magic moment. Activation. You expose the object to its trigger, and you get to watch the programmed transformation happen all by itself. This is all really cool in a lab, for sure. But what does it actually mean for us, out in the real world? This is where it gets really interesting. Let's look at just a few areas that are about to be completely transformed by this. Let's start with healthcare, because the potential here is, well, it's an absolute game changer. Imagine medical stents that can be inserted easily and then expand to the perfect size inside a blood vessel, triggered only by your own body heat. Or implants that don't just fit, but actually adapt and integrate with the body as a person heals. We're even talking about targeted drug delivery, where a capsule only releases its medicine when it senses the specific conditions of the area it's supposed to treat. Now think about construction, about our cities. What if you could ship building components flat packed to a site and they just assemble themselves? I mean, that would slash labor and transportation costs. Or building exteriors that can change shape to control sunlight and temperature, making them way more energy efficient. And in an emergency, imagine disaster relief shelters that can be dropped off as a small package and then expand into a livable structure on their own. And it doesn't stop there. The possibilities really stretch across so many fields. In aerospace, you could have plane parts that reshape themselves mid-flight to be more aerodynamic. In the car industry, materials that can literally self-heal a minor scratch or dent. And for all of us, think about wearable tech that perfectly adjusts its fit, or even packaging that changes shape to be easier to store. Okay, so after hearing all that, you're probably ready to go buy some self-assembling furniture, but we need to bump the brakes just a little. As amazing as all this sounds, we're not quite there yet. 4D printing is still a new technology, and there are some pretty big hurdles to clear before it's everywhere. Really, it comes down to a few major roadblocks. First, you've got the material problem. It's super hard to find a material that's tough, flexible, and highly responsive all at once. Then there's the design complexity. Predicting exactly how these things will change and move in the real world takes a ton of advanced modeling. And of course, like any new tech, it's currently pretty slow and very expensive, which makes scaling up from a cool prototype to mass production a real challenge. But even with those hurdles, the big takeaway here is the incredible shift in how we think about making things. We're moving away from just manufacturing static objects. Instead, we're starting to actually program the physical world around us, creating dynamic, responsive, and almost intelligent systems. And that really leaves you with a final thought, doesn't it? For all of human history, progress has been about building things. But maybe the next chapter isn't about building in the same way at all. Maybe the future won't just be built, it will unfold.